So my name is David Cruzy. I'm the dev lead for the SMB team. I've been working on it for quite a while. And the gist of this presentation is mostly to talk through changes. It's weird. I'm going to go back to doing this. Changes from what we presented at SDC last fall as underneath the umbrella of SMB2.2 and what we call SMB 3.0 now. I can talk a little bit. There's going to be some overlap with what Tom talked about. I'm also going to basically, so after we talk through changes, post-SDC changes to the protocol and answer any questions there, it's also free if you have any questions about the whole SMB 2.2 umbrella. And then you can also find me after the talk if you have more specific ones that require some things. So I mean, as Tom outlined, this was SMB 2.2, and there was a lot there. We did a large session at SDC that was a 2-hour session with Matthew that covered a lot of these points. And all of this carries over from SMB 2.2 into the SMB3 umbrella. And I'm not going to dive in with a lot of detail into this, but there's a lot there, definitely. And if you have questions, ask me. And if I can't answer for some of the other protocols and stuff, we can try and get people here while you guys are here to get your questions answered. So in general, this was the slide from the presentation that talked about the problem space that we were trying to address along the lines of 2.2, and specifically the idea of being storage for enterprise applications. And this is sort of the nice marketing what we want to solve slide. And as Tom outlined in more detail, this was really the justification that went behind this change from 2.2 to 3.0. It wasn't a technical driving anything. It was more about, from a marketing and a perception perspective, we wanted to represent what the big capability changes are. So I can tell you from a code perspective, when we were doing the adaptation, it was a lot of minor string changes and things like that. There wasn't a lot of other structure changes, so hopefully it's not that difficult for you guys as well. And in fact, even the doc is still SMB2, right? It just has 3.0 embedded in it. I don't know if there's any plans to change that. Are we going to do 2,3 MSSMB?
The title has changed, but
has it?
But the identifier MSSMB2 has not.
Okay.
Yeah, the title now says protocol versions 2 and 3.
Right. So, but anyway, the general idea is once all the marketing and people leave the room and it's just the developers, we can say it's still SMB2. You don't have to restructure it. So unless you're trying to get budget approved for your project, then it's a huge change and requires a lot of work. So, but in terms of when you're testing, this is across the Windows 8 releases. We did have to phase it in because there's an implicit incompatibility that comes in when we change the dialect from 2.2 to 3.0. So we kind of took the RC release as being sort of the inflection point that actually speaks. It'll negotiate either SMB 2.2 or SMB 3 on both the client and server side. And it'll treat both of them as what we call SMB 3 right now. So Windows RC will work with beta, or if you have a client implementation that already negotiates 2.2, you can use either beta or RC. If you have a client or server that does 3.0, you can use RC or RTM. But by the time RTM comes out, 2.2 is essentially off the map. It was a pre-release thing, and as far as everything's concerned, it never existed. So here's the main things that or here's the ones that are new since SDC. There's the secure negotiate work that we can talk about that Tom talked through. There's some changes to the signing, and then SMB encryption is sort of the big new feature and stuff. And we can talk about technical details with that, as well as the session key derivation changes. And then channel sequences, I include the slides. We actually forecasted channel sequences at SDC, but they weren't in the code yet. So I grabbed the slide from SDC so that we can talk through it if people have any questions or want any understanding. And then outside of this, there aren't any significant changes aside from, again, the dialect number increase. So once we get through these, we'll just open it up for general questions. So yeah, the intent of secure negotiate is, again, within the SMB2 protocol. It's honestly something that we talked about, and it would have been nice if we had included it from the beginning, but it's to prevent someone in the middle from downgrading the dialect, specifically as feature changes come in that are security related, such as encryption, such as revising the signing algorithm, things that actually have more of a security effect where you could argue if you change the signing algorithm because a previous algorithm or whatever becomes compromised, that you don't want it to be easy to force you back down into the versions that are no longer safe. So this lets us try to ensure that within the SMB2 family, we're always speaking the most recent dialect without actually having to just not negotiate old dialects. So that's the general intent. it does rely on a feature that's in the SMB2 protocol that's not in the SMB1 protocol, which is this idea of the client being able to send an unsolicited sign request, and the server will sign the response. So even if signing isn't active for the session, at any point, the client can say, I want to sign this request to verify that the server gets it and sends me back a signed response. And this feature has been in there for the lifetime of the protocol. And this is where, by having this here, we could choose basically any IOCTL, or in the future, you could add new commands that say, if I want this command to be secure and verified that it reaches a server and isn't compromised by a man in the middle, the client can sign any of these requests. So we added an FSCTL that essentially repacks the validate information. So it includes client capabilities, includes the dialects you support, and the client sends it off to the server in a signed fashion, and it expects a response. Now, if the server doesn't understand the FSCTL, such as, in our case, Vista or Windows 7, the server will fail the FSCTL, but it'll fail it, and it'll sign the failure, which means it had knowledge of the session key so that the server did receive the request and process the response, so it legitimately doesn't support secure negotiate. And clients will accept a signed error as being a successful validation that the dialect was chosen correctly, or they'll accept a signed success response that includes validated information, and then they'll look through what the server returned as what should have been validated and see if it matches what they had actually received in the original validation. Likewise, the server, on receiving the request, will not only return his dialect and capabilities, but he'll verify that what he just received in the validate request matches what you received in the original negotiate request. Yep. So, and here's a slide for Chris. So this talks about downgrading to SMB1, which has been an interesting.
Just for me now, right?
I did. I was right back there. The interesting thing is, again, secure negotiate relies on the fact that the request has to be signed to offer any sort of level of integrity. And with SMB1, it doesn't support this idea of unsolicited sign requests being responded to that was new to SMB2. So if signing isn't enabled, then secure negotiate really doesn't offer you any benefits. Now, if signing is on or required for SMB1, you could issue the FSCTL across and take a signed failure that I don't support it as, again, proof that the server doesn't support it. But with current Windows client implementations, if we fall back to SMB1, the client won't actually issue the FSCTL yet. I think adding this in would be a good next step for hardening. And then what I would assume most servers would do is if you fall back to SMB1 and you're SMB2 capable, you just disconnect if you receive the FSCTL at all. You don't even have to respond to it because you've been compromised, right? Because you failed to SMB1, and the client obviously knows about SMB2 because he knows about it. So the architecture works. The biggest problem is that most SMB1 servers don't require signing or don't even enable signing. So if you fall back to those, what are you going to do? So it's kind of a vague thing. And then another interesting question that would be a nice topic for lunch or dinner or whatever here is, like, at what point do we start to phase off or disable even the SMB1 side of things as support across the ecosystem continues to move forward so that this becomes less of a problem?
So that does bring up then the scenario that would work for a man in the middle would be downgrade the client's request to SMB1 and say you don't support signing.
Well, yeah. So to protect against that, you need either a client or a server that requires signing, not just enables it, but requires signing.
Right, because if the real server requires signing, then it won't allow connection if it is a
yep. So that would prevent it for DCs or other areas or organizations that are already locked down. But requiring signing is less common. Yeah.
Got it. Thank you.
Cool. So that's secure negotiate, and obviously I think there's benefit in implementing it. If you don't implement it, I think we tested with a lot of the devices, and we had email threads in cases where it didn't work. You can just fail it with unsupported, and you don't get the downgrade detection, but this won't actually break. So it's not really, it's sort of optional per se. So the signing algorithm changes. This actually had more to do with overall performance than it did security. It's not like it was viewing that HMAC SHA-256 was inherently insecure. It's just that even on 64-bit processors, the actual processing time it takes to use that algorithm based on how it uses registers and stuff, even in optimized cases, was really high. And if we're trying to push scaling, just so you know, these numbers are non-official. Don't quote me on this. This was measured on one person's machine when we were doing some of the evaluations. But on modern processors, as Tom called out, there's new capabilities where for some of the other algorithms, we can offload a lot more of the work and do larger calculations. So we did some evaluation as we were doing when we get to encryption, we'll look at it. We were doing encryption and doing some measurements, and we realized that it was cheaper in cycles per byte to encrypt than it was to sign. And we're like, wait a minute, that doesn't make any sense. And then we looked back at signing algorithms. We realized if we use the AES CMAC on the modern server processors, what this number is. So I don't know if you guys are familiar with cycles per byte as a measurement. It's something we toss around a lot. But basically what we're doing is we're measuring based on, in this case, it's packet sizes that you're either sending or receiving, how many processor cycles it invests based on the number of bytes in the message. So what this is kind of saying is that for this algorithm to basically set up and initialize, you're paying about 6,500 cycles, plus about 18 cycles per byte of data that you actually sign. And when we moved on to the new algorithm on our system with the implementation, you can see that it was actually cut in about a third. So in terms of, again, pushing signing out to larger scale or larger scale servers, this could really cut down on the overall costs. So, but yeah, plugging this in should be pretty simple. Encryption was probably the bigger feature to come in after SDC, and it's definitely one that I think is going to see a lot of use. And it's, I mean, the goals are pretty obvious that we want to provide sort of this end-to-end encryption of the data in flight. And there have been stories going back and forth in a constant debate saying, well, there's IPsec out there, why do we need this and that? But we just know from a customer's perspective that IPsec is difficult to deploy, it's not common, and this is just dead simple, right? It uses all the keys that we already authenticate through through Kerberos, the same way we do session signing, and in terms of scenarios people use it, the main ones we've been looking at are probably WAN or branch offices, but I wouldn't be surprised if people just start setting this on HBI data and every other system, or if you're moving source code around, or any of those places where you want data to sort of be secure in transit. The algorithm here, again, uses the AES-CCM. There's not an algorithm negotiation capability right now, but when we get to the packet field, you see that there is an algorithm identifier. The architecture is made to be pluggable so that you could put in sort of any transform algorithm in the future. This was just the one that could sort of fit in within the timelines we were looking at. And a note about the algorithm is it does sign and encrypt the data. So even if SMB signing isn't on, when you go through the encryption phase, you get an encryption, and then you get a signature of the encrypted data. And what this does mean is that an encrypted packet is considered signed. So if you have a server or client that requires signing, but you have a share that requires encryption, if you encrypt the packet, you don't have to sign it as well. You do one or the other. You don't need to do both of them. And again, from a performance perspective, if you compare this to the HMAC SHA-256 of SMB2.1 and earlier, the cycles per byte is actually lower in encryption than it is in signing. I think the numbers we had is around 8 cycles per byte on some informal measurement. So you can test it as well. And that, again, has to do with using some of the accelerated features available in the modern processors and stuff. But it's kind of interesting to think that encryption can actually be cheaper than what we would pay for signing in the past. For interopt, if you have a server or a share that requires encryption and you get downgraded, or you have a down-level client who's sort of coming in, they basically get access denied. So for encrypted shares, you can't access them from down-level clients. There is, I think there's a setting or a registry key we might have supported that was allow access to encrypted data from down-level protocols. So it was more of a test or deployment blocker when people had these mixed modes and they wanted to play around with it, where they could turn it on, and then you can come in as an older dialect and actually still access the data. But obviously, that's not how we expect people to deploy it, because it kind of ruins the whole point if people can access
David,
it.
we actually describe those bits in the document now as Windows behaviors.
Okay, so there are, yeah.
There's 2 bits, and they interact in funny ways.
Right, so there's 2 bits, it sounds like, Tom points out in the document that talk about this idea of allowing unencrypted access to encrypted data. So, but in general, I would just, only do those if you need the workarounds and stuff like that. I don't think it's something that we expect customers to adopt heavily. In terms of when encryption sort of turns on and turns off, again, there's 2 modes. You can have a server that is marked as requiring encryption, or you can leave the server as just a normal server and then mark individual shares as requiring encryption. So if server-level encryption is on, then that's returned basically as part of session setup capabilities, and every packet that would be sent by that session after session setup would be encrypted on the wire. For share-level encryption, this would be after tree connect phase. All packets sent by that session on that tree connect are encrypted. What this does mean is when you're looking at sniffs, it wouldn't be uncommon to see a mix of encrypted and clear text traffic on the same connection, because again, it's based on the properties of the of either the share or the session. And none of the unsolicited responses from the server, specifically lease breaks or op block breaks, are encrypted using the current model. There's no dependency on auth package with respect to encryption, because again, we take the session keys that fall out of authentication, and both NTLM and Kerberos provide session keys. And as well, I guess, so SMB3 packets are sort of described implicitly. If you're using RPC over named pipes now, because again, you flow over SMB, that'll be natively encrypted as well if you have a server that requires encryption. So protocols that sit above the SMB layer can take advantage of this. If you're doing SMB direct and RDMA, the one note is that we will encrypt the packets sent through the send and receive path, but any data moving along the direct data channels using SMB direct read and write operations is not encrypted. Does that make sense? So once you get into that mode, it's kind of interesting to figure out why you're using SMB direct for direct data placement, but you want to do double copies and do encryption decryption. I don't know. I don't think that's going to be a bit. So this is a quick snap from the doc of what the transform header looks like. So if you're doing network monitoring and you're running into encrypted packets, what you're actually going to see is this, which starts with the FD SMB as opposed to FE SMB for SMB2, followed by these individual fields. Ones of interest are there's actually the encryption algorithm identifier, which right now must be set to the AES CCM. And then nonces are essentially generated by the client or server. All these are, you'll basically find these are the inputs that go into your actual encryption algorithm. And it's described in the doc. And then there is a session identifier. And this is how you actually identify the user who's encrypted the data. Similar to signing, you're not negotiating an encryption channel for the entire connection. You negotiate you're not negotiating, or you're not encrypting on behalf of the entire connection. You encrypt on behalf of the user who initiated the packets. Does that make sense? So it's per session encryption. So if you do multiplex multiple sessions onto the same connection, you will be switching keys based on which user is sending a packet. So
The FD is specific to the encrypted transform header.
sorry, what was that?
The OXFD, that's specific.
Yes, yeah. So FF was SMB1, FE
Yep.
was SMB2, and FD is the transform header.
So that's weird.
It's -1, -2, -3. We're counting down.
So the encrypted frame from the OXFE header on down will be on the tail end of this, right?
Yes, sorry. So this is the header, and then basically what would packet here is, or what would follow here is a message size, which is the full encrypted buffer, and that would include the SMB2 header, the SMB2 request, and any sort of payload data that goes with it.
Okay.
And
That's what my question is: how do I know how much to read off the wire before I decrypt it?
Well,
so
the SMB packet has basically a message length header, which indicates
Right.
the entire size of this, and then encoded in here is the original message size as well.
Okay, so that part is not encrypted.
No, this part is not encrypted, but this
No,
part
so-
is.
Sorry, the part that tells you the message length of the encrypted.
Oh yeah, sorry. So that precedes the message from a stack layer. So that's
Okay.
we call it
Maybe I'm
the
getting
direct
that
host
here.
TCP. There's like a U-long that indicates overall message size. So
Okay.
that size would actually say the whole message.
Gotcha.
Yeah.
Gotcha.
And then this would come here.
Okay, that makes sense.
So, and we do include original message size because you might have cases as we move on to different algorithms where the size of the encrypted payload gets rounded up or down, and you need to know how much the original message was.
Gotcha. Okay.
Yes.
So the signature field inside the data that's encrypted will always be zeros, will always be.
Yes.
running.
So yeah. So the question is, for the SMB signing field inside the encrypted payload will always be 0. That's correct. And to be clear, this signature is essentially the signature of this
Yeah.
packet as well as the
Yeah,
encrypted
yeah.
packet. So the whole thing is sealed up nice and secure. So
That included, so you said you went like this, and I'm just.
No, it's all of it.
It's
Has
all
to be-
including
has to
the
be all of
Yeah,
it.
FDS.
yeah.
Has to be all of it, otherwise
Right.
you change the other part.
yeah. So cool.
Can you share the paper? That makes sense.
Well, yeah. So
Theoretically,
you could garble it, but you couldn't construct it per se. And actually, the server would reject it. I guess you're right, because if you changed it when we went to validate it,
It's better to sign the whole
This,
thing, but. yeah.
this signature attacks.
yeah,
You
So.
never know what people are capable of these days.
definitely. One of the changes here that came in with encryption, and you could argue it's interesting in RPC, is this idea of using a key derivation algorithm to actually derive different keys for signing as well as encryption. There's two for encryption, one going client to server and one going server to client. And then we actually separated out the session key we give up to RPC or user mode applications. The idea here is that we didn't want, I'm not a cryptographer, I'll say that first, but there's very few studies that say, okay, if I can see the result of you signing a packet and I can see the result of you encrypting a packet, since you're using the same key in two different algorithms, can I use the result of those two algorithms to try and derive the key back? And it's not that it's possible or not possible, it's just that they don't really study it. So what they recommend is you actually don't use the same key for different algorithms. So now you'll see through here that the original session key that was returned from Kerberos or NTLM is classified as private, and that's held internal on the server and client if you're negotiating in SMB3. And from that, you derive different keys for signing, encryption, and a session key using a one-way formula, and then those can be used, and we don't have to worry about any of these sort of coordination, collaboration attacks that sort of span different algorithms. So that's just another RFC you'll have to implement to derive out the keys, with just a set formula call to move through. So, and then the last one that was new from SDC, and this is a slide from Matthew's portion of the talk that talked about the channel sequence numbers. So this is used for mostly to give some context, because again, I guess I'm jumping through this. The issue here is in multi-channel replay scenarios, you can have these ideas of write-write conflicts where you have an operation that's in flight, the client gets disconnected, client is going to retry the operation on another channel, but he needs to make sure that the replay of the operation doesn't get executed on the server before the original operation is drained out. Because if it does, the sequence of operations would be, I issue a write that's going to write the letter A, I get disconnected, I reissue a write that's going to write the letter A, that succeeds, I reissue a write that's going to write the letter B, that succeeds, but my original one writing A was hanging out in a queue somewhere, and now that gets processed overwriting B with A, and now I've corrupted data. So what I need to verify is that when I'm doing replays or initiating new operations, that previous operations have successfully drained out of the queue. The way this is done, there's the channel sequence field that Tom pointed out inside the SMB header. And the nice thing about it is the client actually has knowledge when we're replaying operations, when a disconnect has occurred or something like that. So the series as we walk through this is the client, we'll say we're starting at epoch level 5, which means changes have happened in the past. So if I'm issuing a write, and what the blue line here is it's actually showing that write executing on the server. The most common thing that happens is the write might execute pretty quick, but now we're trying to send the response back to the client. But it could also be that this is a really slow file system where this gets hung up in a queue somewhere, and it's basically waiting to be processed down here. And at this point, the client detects a channel failure in multi-channel. So the client knows he has another channel over here that's already set up with multi-channel, and I can retry it right away. I'm going to skip the read right here. I'm going to jump right down here. So, but I also know a failure occurred. So for this object, we do it at a per open basis. I can say, well, let me increment the epoch number, because I know a failure has occurred. So now I'm going to start using the epoch number, which is 6. And when I replay the write, I'll set the replay flag, and I'll set the epoch number to 6. When the server receives this, he can basically see that there's operations pending that have an epoch less than 6, and he can fail it saying, this file is not available yet because there's operations in progress. From an implementation perspective, you could also pen this over there for a little bit if you wanted to try and optimize it. From our side, we don't like to hold state on the client. We've been preferring that or on the server, we've been preferring that the client retry. You'll sort of see that consistently in a lot of the CA things. So he can do a quick check here that says there's operations in flight. This is a state modifying operation. The object has operations in flight that have an epoch less than 6. So I can mark the current one as 6, but I'm going to fail this until operations less than 6 drain out. Eventually, I get a send failure here, or I detect a channel failure. This operation completes. And now when the client replays it, I can say, OK, now it's at epoch 6. There's no operations running with less than 6. So I can return success. Calling out the read here, what this is showing is that non-state modifying operations that aren't replays don't actually have to pend, because inherently they're allowed to flow. The client's letting this read flow before that write completes, so he thinks it's fine if these two operations race, so the server isn't required to serialize those two. That's just showing some of the complexities. So it sounds complex, but in the end, it ends up being quite simple, because the majority of the cases, the client is well connected and the state isn't changing, and you're just doing a quick check and realizing that your state on the server is that you're at the same epoch number and there's no operations pending, and you just sort of move through. And it's only in cases where these channel failures start to arrive that you start having to do this various serialization. So this was in SDC with a big tag saying, this isn't in the beta builds yet. I'm just saying that this did come in after SDC, so RC has this behavior, as well as the replay flag, which used to be a create flag, was moved to be a general SMB2 header flag. So whenever the client replays an operation, we do tag them as replays so that you can see that they're happening. So that's essentially all the changes post SDC. There's a lot, obviously, that was at SDC as well, too. So at this point, I was just going to open it up for if people have questions either about the specific things we've talked about or about any of the other features, and I'll do my best. And likewise, if they're overly complicated, we can either take them into lunch or pull in the people necessary.
So Dave, if you have to summarize the difference between IPsec and SMB encryption, what would it be?
So the question was, if I had to summarize the difference between IPsec and SMB encryption, what would it be? I mean, IPsec is a very, it's generalized. It supports dynamic algorithm negotiation. It has a lot of stuff. I don't want to say bad things about it. That being said, SMB encryption, the goal was to be as easy to deploy as SMB signing is. This is just a bit that you turn on, and you don't even have to worry about it. So it's much simpler. It's hard-coded to a specific algorithm right now, but deployment is really, really easy. So I think that's the big difference, is it was trying to take away the complexity of, do I have to do any certificate management? How do I deploy this? How do I roll it out? And just make it sort of a brain-dead simple turn on, as well as there are some customer sites where, honestly, no matter how much you talk to them, they're not going to deploy IPsec.
IPsec is very thinly deployed, and there's no way that SMB could depend on its presence for such an important feature. So that's one problem. Second, it's not necessarily end-to-end. SMB encryption is end-to-end, right? It's from the client all the way to the server, no matter what's in the middle. And that's really important. And then finally, as David said, it's integrated with all the authentication and existing keying of SMB, so there's no additional management required. It's very, very easy to deploy.
So it's going off of the session key.
Yes.
Derived, right? That SP800, whatever
Yeah.
this thing. The key derivation is critically important to leverage the existing keying that's going on for the authentication subsystem. IPsec would be a totally separate thing on the side that would not solve the full picture.
A few questions on secure negotiate feature.
Okay.
One is, when does it happen? And second is, can it happen multiple times on a given connection?
So for secure negotiate, technically the client could issue the IOCTL or FSCTL code whenever it chose to, and the server would respond in kind. Our client will issue it, I believe it's after the first tree connect, and we'll do it a single time for a given connection. In multi-channel scenarios, I don't believe we do a second round of negotiate validation, because essentially we've gone through a session binding, and we will internally make sure that the negotiate of the second connection matches the result of the negotiate of the first connection. And then we do the session binding, which is secure as well, that assures it's the same target, and then that's good enough for us. So I believe you will only see it after the first tree connect on the original connection from the client.
Okay. One question about the encryption. How does it interoperate with signing? Let's say I have signing enabled as well as encryption enabled.
Right.
So how does it? How does my packet look like in that case?
So what would happen if it's server level encryption? Then that basically goes active after the completion of the session setup, which is the same time that signing would normally go active as well. So if server level encryption is on, then you would see every packet following session setup to be encrypted, and when you decrypt it, the internal packet would actually not be signed. The signature key would be 0, because encrypting it is an implied signing action, because there's a signature validation of the encryption. We don't do both. If you had a server that requires signing, and then you were accessing multiple shares, but only one of them required encryption, what you would see is the packets bound onto the tree connect for the encrypted share would again be encrypted, and then the packet, the ciphertext within the packet when you decrypted it would not be marked as signed, but should be treated as signed by the server. There's no basically we never both sign and encrypt a packet. That's a simple one. We either sign it or we encrypt it, and from a server side or client side, encryption is implied signing. So Does that make sense? Cool. Any other questions?
Encryption makes troubleshooting and debugging kind of hard, right? Like when you're developing this, you get a packet trace from a customer, it's all encrypted. You have no idea if it's server level, what happened in the tree connect and.
Right. Yeah. So with respect to debugging, like we have our like the internal WPP tracing stuff, and then we actually have some event channels that we need to look through that will actually log some packet data as well. And there's been some where we're trying to figure out easier ways for people to actually get the clear text translation of those packets as well. I don't know if there's anything that's public yet that we're talking through, but I think it's a common problem. And I'd say from our own implementation, there's ways that we can sort of obtain that information post decryption step or pre-send, and I would advise that everyone's probably going to end up doing the same thing. But now you are going to have the issue, like if you can't like sniff on the gateway or hub machines or whatever like that, right? Everything has to be on one side or the other. So.
Okay.
Yeah, by design, you cannot sniff in the middle of the network. But there are some there are some tools, and I'm looking around the room for the WinterOp folks because they're really the ones who can speak to this. But tomorrow, you should hold your question until tomorrow because SMB encryption and SMB direct, the RDMA, are two really interesting, basically uncapturable scenarios, right? And there are some facilities in Windows that David just mentioned, the event channels, that will allow that. And there also are some tools under development to help analyze those event channels. But we need the tomorrow's talks to go into that.
About the encryption again, if there is a Quas device, how does it interoperate with it?
So is this like a WAN accelerator style device or something in the middle, or?
No, it might be stateful firewall that sits between the networks.
I mean, that's an interesting question because, again, it can't see what the interior of the packet is. It'll know it's running across like TCP 445, but even from the very header beginning, I don't know if it'll classify it as an SMB or an SMB2 packet if it's not transform header aware. So this might be up to the individual device what it does with interior or with unrecognized packets. So, but I'd imagine the eventual goal should be it'd be similar to if you were doing SSL across each device, where it can't actually see inside. That it's going to have some policy that says whether I allow this or not. I don't know if we haven't had any reports of interrupt concerns, but I don't know if we've been actively going out and pursuing testing with those devices either.
There's another interesting question for Quas devices. There's another interesting question for Quas devices, and that's multi-channel, which then puts all kinds of different user streams and different tree connects on the same socket, right? Or even starts connecting multiple sockets over multiple non-shared links, right, by design. And so Quas devices and really traffic shaping that kind of aggregate flow are going to be pretty interesting. And I mean, I would love to hear a Quas device vendor give some thoughts on that. But yeah, it'll be an interesting development, I think. If you turn off multi-channel, the Quas problem becomes a lot easier. But maybe it's not as compelling without multi-channel. We don't think so.
Yeah, so from the multi-channel side, the point that Tom's talking about, just to make sure everyone knows, is that pre-multi-channel on SMB2, we would have one connection per session, and any connection would only ever have one session. So the protocol supported multiplexing, but from a Windows client perspective, we never did it. With multi-channel, what ends up happening is if you have a large number of sessions, the client will create a pool of connection and bind all the sessions across those connections. So any connection could have a series of sessions bound to it, and in fact, the relationship of connections to sessions can be a many-to-many relationship. So that sort of clarity that says there's one socket per user really goes out the window. Now that being said, for scenarios like, say, IIS, where you're establishing 1,000 sessions or whatever, your efficiency will go up because you're not going to have 1,000 sockets. You're going to have a pool of, what is it, like 16 connections or 8 connections, however we do, and you're going to be subdividing the load across those.
So multi-channel is only when have a multiple paths, correct?
Well, the multi-channel will go if there's multiple paths, or if you have an RSS-capable adapter. We will establish multiple connections on the same path to take advantage of the ability to sort of scale across CPUs and stuff. And there's actually other interesting cases it kicks in. if you have the wireless adapter now, and you plug your laptop in actually, because now you technically have two paths, and we recognize arrival, it'll actually query the server and it'll switch over. And then if you unplug it, it'll switch back. So it's fun. The client guys were surprised by this because we didn't design it for them, but it worked for them.
So. There is one other interesting thing about multi-channel. As David mentioned, even with a single connection, funny things happen, right? We'll still share, with a single connection, we'll still share sockets over that one connection. When it really gets interesting is when there's multiple connections. And in the wireless case, it's clear to the client and server that they're two very different things, right? Different speeds primarily. But what if they're the same speed, right? It'll start trunking them. And so connections for, requests on a given session will actually start flowing over multiple connections. So you won't see a single stream of requests necessarily on a single connection. You have to sniff all those links and all those four tuples to see the aggregate flow. And that's another interesting packet filtering thing that I hope the WinterOp folks will talk about.
So you used to have multiple channels over a single transport, but you never, Windows implementations never implemented it. Is that what you're saying?
Well, so the question was, did Windows implementations ever multiplex multiple sessions across the same connection? So on SMB1, we did. And SMB1 was confusing because by default, it would multiplex sessions onto the same connection unless you turned on terminal services and there was some little reg key that would get flipped or then that would turn off. But then when, what was it? Was it XP or Vista came along, it switched back and it started now always using the same connection and multiplexing again. And it sort of hopped around. SMB2, the consistent story was that we wouldn't multiplex, although the protocol was designed to support it. It's sort of an implementation choice. And now it's sort of moved back to a much more complicated world, which is, well, you kind of multiplex, but it's many to many now. And it's more.
And the use of these channels in an are implementation dependent.
Yeah, the algorithms for load balancing and how we select. I mean, from the server side, you accept the message on whatever connection that the client selects. So this is really more of a client policy and how it chooses to load balance. Right. And from our side, it's an interesting part to do a lot of optimization and stuff like that, especially.
There are no limitations in the protocol about the usage of the channels.
No, yeah, there's no requirement, so clients can use it. And even, like, if you look at policy-wise, we'll only use adapters which are equivalent, because it's like, how do you load balance, 1 10 gig and 5 1 gig? It's like, what's the algorithm? When do you stop using the 10 gig and start using the 1 gig adapters? It's just really complex. So for simplicity, we just say, we're going to pick the family of adapters that have the same sort of bandwidth and properties, and we're going to use all of them and load balance between them. And we will fall back if those get disconnected. So we'll fall back from the 10 gig to multiple 1 gig and stuff like that. But theoretically, a client could choose to use all the paths available and come up with some fancy algorithm that says that sometimes the 1 gig is faster. I don't know.
That's described. That behavior is described in a behavior node in the new preview. So if you really want to go crazy, you can try to study that and figure out what'll happen. But yeah, I believe it's accurate.
So just to capture that, Tom said that that's kept in a Windows behavior note in the SMB2 preview that you all referred to, which is on the preview note on MSDN.
And is there another question? On the SMB Direct side, I did pull up. This was the most recent one I think Tom was hinting at. That was showed at Tech Ready for RDMA, where they were at 10.3 gigabytes per second with 4.6% CPU. I think that was one. That's the current public best and stuff. So, and definitely when you get into RDMA, the load balancing stuff gets interesting because the latencies are so low and the bandwidth is so high and stuff. So that's the biggest number so far. So cool. Any other questions?
Well, thanks, David. And David's presentation will be on Channel 9 here soon. All of the previous SMB presentations from the previous Plugfest are included as well, so you can refer to those. And if you have questions, of course, you met Tom, the architect from the team, SW earlier. We also have Sai and Prasanna from the documentation team working with Tom, and a number of our escalation engineers, test resources. There will be others from the test team here today. So if you have questions, please take advantage of these opportunities. We realize there's a number of components. Tom described a whole series of protocols. So there are owners to these at this event, but if you need to find the owner for that protocol, let us know. It's a rather complex set of pieces. So thank you. Thanks, David.